U. In 1964, physicist John Stuart Bell published a paper that would quietly become one of the most important turning points in the history of science. At the time, quantum mechanics was already successful beyond dispute. It accurately predicted the behavior of atoms, electrons, light, and matter with astonishing precision. Yet many physicists, including Albert Einstein, remained deeply uncomfortable with what the theory seemed to imply about reality itself. Quantum mechanics described the microscopic world in terms of probabilities rather than certainties. According to the equations, particles did not always possess definite properties before measurement. Instead, they existed in a spread of possible states, only producing a specific outcome when observed or interacted with. To Einstein, this sounded incomplete. He believed that beneath quantum uncertainty, there had to be a deeper layer of hidden physical reality, variables we simply had not discovered yet. In Einstein's view, nature should obey what physicists call local realism. Realism meant that physical properties exist whether or not anyone measures them. Locality meant that objects could only be influenced by their immediate surroundings, not by events happening instantaneously far away. This disagreement led to one of the most famous debates in modern physics. In 1935, Einstein and his colleagues Boris Podolsky and Nathan Rosen proposed a thought experiment designed to expose what they believed was a fatal flaw in quantum mechanics. The paper became known as the EPR paradox. The argument centered on a strange phenomenon now called quantum entanglement. When two particles interact under certain conditions, quantum mechanics predicts that their properties can become linked. Measure one particle and the result is correlated with the other, even if the two particles are separated by enormous distances. Einstein found this deeply troubling. If measuring one particle instantly determined the state of another distant particle, then either information was somehow traveling faster than light, or the particles had secretly carried predetermined instructions all along. Einstein favored the second explanation. He believed the particles already possessed definite hidden properties before measurement. For decades, this remained a philosophical dispute because there was no practical way to test it experimentally. Then Bell changed everything. Believes that Einstein's idea of hidden variables was not just philosophy. It produced measurable predictions. If local hidden variables governed reality, then correlations between entangled particles would be limited in specific mathematical ways, Belarev inequalities that any local realistic theory would have to obey. Quantum mechanics predicted those inequalities could be violated. That meant the debate could finally move from philosophy into experiment. Bell's insight transformed a conceptual argument into something physicists could actually test in the laboratory. And when researchers eventually performed those experiments, the results stunned the scientific world. Beginning in the 1970s and continuing through increasingly sophisticated experiments in the decades that followed, physicists repeatedly observed violations of Bell's inequalities exactly as quantum mechanics predicted. The most famous early confirmation came from Alan Aspect and his team in 1982. Using entangled photons, they performed measurements under conditions designed to rule out ordinary classical explanations. The results strongly supported quantum mechanics and contradicted Einstein's as local realist picture. Later experiments became even more precise. In 2015, independent teams in Delft, Vienna, and at NIST in the United States carried out what are known as loophole-free Bell tests. These experiments closed the major technical gaps critics had pointed to for decades. Once again, the outcome agreed with quantum mechanics. The conclusion was extraordinary. Nature does not behave according to classical local realism, but this is where many popular explanations become misleading. The experiments did not prove that consciousness creates reality. They did not show that humans can influence distant objects with thought, and they did not demonstrate that space is an illusion in the everyday sense. What they showed is more subtle and in many ways more profound. Quantum entanglement reveals that the microscopic world cannot always be described as a collection of separate independent objects carrying fixed properties through space like tiny billiard balls. Instead, quantum systems can display correlations that are deeper and stranger than anything allowed by classical physics. At the same time, entanglement does not allow faster than light messaging or communication. Physicists cannot use entangled particles to send usable information instantly across the phase. Instantly, Einstein's theory of relativity still stands. What changed? U was not the speed of communication, but our understanding of what reality looks like beneath ordinary experience. And that is why Bell's theorem matters so much. It forced physics to confront the possibility that the universe is fundamentally different from the intuitive mechanical picture humans evolved to understand. At microscopic scales, reality appears governed not by certainty and separation, but by probabilities, relationships, and quantum states that resist classical explanation. The deeper meaning of those results is still debated today, but the experiments themselves are no longer in doubt. To understand why Bell's theorem changed physics so dramatically, you first have to understand the problem that haunted quantum mechanics from the very beginning. In the early 20th century, physicists discovered that the microscopic world behaves nothing like the world we experience every day. Electrons did not move like tiny planets orbiting a nucleus. Light behaved both like a wave and like a particle. At the quantum level, certainty seemed to disappear entirely. The new theory of quantum mechanics was incredibly successful at predicting experiments. But even many of the scientists who helped create it struggled to accept what it appeared to say about reality. Among them was Albert Einstein. Einstein was not opposed to quantum mechanics because it failed experimentally. In fact, he helped lay some of its foundations. His discomfort came from its philosophical implications. Quantum mechanics suggested that particles do not always possess definite properties before measurement. Instead, the theory described reality using probabilities. An electron, for example, could exist in a range of possible states until an interaction forced a specific outcome. To many physicists, this was simply how nature worked. To Einstein, it sounded incomplete. He believed the uncertainty in quantum mechanics reflected missing information rather than true randomness. Somewhere beneath the U equations, he suspected there must be hidden variables determining the outcomes in advance. Einstein summarized his objection with one of the most famous lines in science: "God does not play dice." The conflict became sharper in 1935 when Einstein, together with Boris Podolsky and Nathan Rosen, published what is now called the EPR paper. Their goal was not to destroy quantum mechanics outright, but to show that it could not be the final description of reality. The argument centered on a strange phenomenon now known as quantum entanglement. Imagine two particles created together in such a way that their properties become linked. According to quantum mechanics, measuring one particle instantly determines the correlated outcome of the other, even if the particles are separated by vast distances. At first glance, this sounds manageable. After all, ordinary objects can also carry correlated information. If you place a left glove in one box and a right glove in another, then send the boxes to opposite sides of the planet. Opening one box immediately tells you what is inside the other. But Einstein argued that quantum mechanics was claiming something fundamentally different. In the glove example, the gloves already possessed definite identities before anyone opened the boxes. Quantum mechanics, however, implied that particles might not possess definite properties before measurement at all. That distinction disturbed Einstein deeply. If the particles did not already contain predetermined properties, then measuring one particle seemed to instantaneously affect the other regardless of distance. Einstein famously dismissed this possibility as spooky action at a distance. Why was that such a problem? Because it appeared to conflict with one of the central principles of relativity. No influence should travel faster than light. Einstein believed reality should obey what physicists call local realism. Realism meant physical properties exist independently of observation. Locality meant objects are only influenced by their nearby surroundings. Quantum entanglement appeared to threaten both ideas. For decades, physicists argued about the issue without resolution. Some accepted quantum mechanics as complete. Others believed hidden variables would eventually restore a more intuitive picture of reality. Then in 1964, John Stuart Bell made a breakthrough. Bell realized the debate could be settled experimentally. He showed that if local hidden variables governed reality, then measurements performed on entangled particles would obey precise mathematical limits. These limits became known as Bell inequalities. Quantum mechanics predicted something radically different. Under certain measurement conditions, entangled particles should produce correlations, stronger than any local hidden variable theory could allow. In other words, if experiments violated Bell's inequalities, Einstein's classical picture of local realism could not fully describe nature. Bell had transformed a philosophical argument into a measurable scientific test. This was revolutionary. For the first time, physicists could experimentally compare two competing visions of reality: a universe governed by hidden local properties, or a universe behaving according to the strange, non-class predictions of quantum mechanics. When the experiments were finally carried out, the results repeatedly favored quantum mechanics. Bell's theorem did not prove that faster-than-light communication exists, nor did it prove mystical ideas about consciousness or universal unity. But it did show that the microscopic world cannot be explained entirely through classical local hidden variables. That realization forced physicists to confront a difficult truth. Reality at the quantum level does not behave according to ordinary human intuition, and the deeper meaning of that fact is still being debated today. By the late 20th century, the debate over quantum mechanics had moved beyond philosophy and into the laboratory. For decades, scientists argued about whether the strange predictions of quantum theory reflected something truly fundamental about reality, or whether hidden variables might eventually restore a more classical picture of the universe. John Stuart Bell had shown that the disagreement could be tested experimentally through what became known as Bell inequalities. Now, physicists needed to perform the experiment. The challenge was enormous. Quantum effects are delicate, and entangled particles are notoriously difficult to isolate and measure. Early experiments in the 1970s hinted that quantum mechanics was correct, but critics argued that technical flaws called loopholes prevented definitive conclusions. The most famous breakthrough came in 1982 through experiments led by Alain Aspect in France. Aspect and his team generated pairs of entangled photons and measured their polarization after separating them in space. Crucially, experimental setup rapidly changed the measurement settings while the photons were already in flight, making it far harder for any hidden classical mechanism to explain the correlations. The results were striking. Bell's inequalities were violated exactly as quantum mechanics predicted. The particles displayed correlations stronger than any local hidden variable theory should allow. This did not mean the particles were secretly sending messages faster than light. In fact, quantum mechanics still prevents entanglement from being used for faster-than-light communication. No usable information can be transmitted instantly through entanglement alone. That distinction is critical. Many popular explanations exaggerate the results by claiming that everything is instantly connected or that distance does not exist. The experiments did not prove those things. What they actually showed was more precise and more scientifically important. The behavior of entangled systems cannot be fully explained by classical local realism. That statement has profound consequences. Classical physics imagines the universe as a collection of separate objects, each carrying definite properties through space and time. Bell experiments showed that this picture breaks down at the quantum level. Entangled particles behave as parts of a shared quantum system rather than as fully independent objects with pre-existing instructions. Over the following decades, experiments became increasingly sophisticated. Researchers improved detectors, increased distances between measurements, and tightened control over timing and random measurement choices. Yet the results never changed. Again and again, Bell inequalities were violated in agreement with quantum mechanics. Still, skeptics pointed to remaining loopholes. One loophole suggested that detectors might selectively miss certain particles, biasing the data. Another argued that hidden signals traveling slower than light might somehow coordinate the measurements if the timing was imperfect. Others questioned whether the measurement settings were truly random and independent. Physicists responded by designing even more rigorous tests. In 2015, 3 major research groups, one in Delft, another in Vienna, and another at NIST in the United States, performed what became known as loophole-free Bell tests. These experiments simultaneously closed the major loopholes that critics had debated for more decades. Once again, the outcome supported quantum mechanics. The conclusion became extremely difficult to escape. If the experimental assumptions are valid, then local hidden variable explanations cannot fully describe reality. But this is exactly where careful science communication matters. The experiments did not prove that consciousness creates the universe. They did not demonstrate telepathy, cosmic unity, or mystical energy fields. And they did not show that everyday space and distance are illusions. Humans scale reality. You still obeys classical physics extraordinarily well. Planets orbit stars. Light takes time to travel. Causes still precede effects in ordinary experience. Quantum mechanics does not erase those facts. Instead, Bell experiments reveal that beneath the classical world lies a deeper quantum structure that does not behave according to ordinary intuition. Physicists still disagree about how to interpret that structure. Some interpretations suggest particles lack definite properties before measurement. Others describe reality in terms of relationships between systems rather than standalone objects. The many worlds interpretation proposes that all possible outcomes occur in branching, quantum histories. Other interpretations attempt to preserve realism in different ways. Importantly, the experiments themselves do not choose between these interpretations. They only rule out certain classes of local hidden variable theories. That distinction is often lost in sensationalized explanations. The true achievement of Bell experiments is not that they proved science fiction ideas about reality, it is that they forced physics to confront a universe stranger than classical intuition ever imagined. At microscopic scales, reality appears governed not simply by isolated objects moving through space, but by quantum states, probabilities, and correlations that challenge our deepest assumptions about separateness and certainty. And despite decades of research, physicists are still trying to understand exactly what that means. By the 1990s, physics faced a problem that had resisted solution for decades. The two greatest theories in modern science, quantum mechanics and general relativity, both worked extraordinarily well. Yet, they described reality in fundamentally different ways. Quantum mechanics governs the microscopic world of particles and fields. General relativity, developed by Albert Einstein, explains gravity, space, and the large-scale structure of the universe. Each theory has passed experimental tests with incredible accuracy. But when physicists try to combine them under extreme conditions, such as inside black holes or at the beginning of the universe, the mathematics breaks down. This conflict pushed researchers toward one of the strangest ideas in theoretical physics: the possibility that space itself may not be fundamental. One major clue emerged from black hole research. In the 1970s, physicists studying black holes discovered something deeply unexpected. Black holes appeared to obey thermodynamic laws. They possess temperature and entropy, meaning they somehow stored information. The surprising part was how that information scaled. Normally, you would expect the information content of a region to grow with its volume. A larger box can hold more stuff than a smaller box because it contains more space inside. But black holes behave differently. Their entropy appeared proportional not to their volume, but to the surface area of their event. Horizon. This strange result led physicists like Gerard T. Hooft and later Leonard Susskind to propose the holographic principle. The idea was radical. Perhaps the information describing a three-dimensional region of space could actually be encoded on a lower dimensional boundary, much like a hologram stores three-dimensional images on a two-dimensional surface. At first, this sounded almost absurd. How could a universe with depth, distance, and volume emerge from lower dimensional information? Then in 1997, Juan Maldacena introduced one of the most influential developments in modern science, the ADS/CFT correspondence. This mathematical framework suggested that certain gravitational systems in higher present dimensional space could be exactly equivalent to quantum theories defined on a lower dimensional boundary without gravity. In simple terms, two seemingly different descriptions of reality could represent the same underlying physics. The idea became one of the strongest realizations of the holographic principle ever discovered. But this is where careful explanation matters. Popular science discussions often exaggerate the implications by claiming that the universe is literally a simulation or just a hologram. That language is misleading. The holographic principle is not evidence that reality is fake, computer-generated, or created by consciousness. Instead, it is a mathematical insight suggesting that the geometry of space may emerge from deeper U-formational relationships. Physicists are not saying that tables, stars, or galaxies are illusions. They are exploring whether spacetime itself could arise from more fundamental quantum and structures beneath it. That distinction is essential. The holographic principle remains an active area of theoretical research, not an experimentally confirmed description of the entire universe. While the mathematics behind AD/CFT has been enormously successful in certain contexts, scientists still do not. You know whether our own cosmos works exactly this way. Even so, the idea has transformed modern physics. It suggests that space may not be the ultimate foundation of reality, but rather something emergent, a large-scale feature arising from deeper quantum relationships. This possibility connects to a broader trend in theoretical physics. Increasingly, researchers suspect that concepts humans experience as fundamental space, locality, perhaps even time, may emerge from more primitive underlying U structures. Quantum entanglement appears especially important in this picture. Some modern approaches suggest that patterns of entanglement may help generate the geometry and cache of spacetime itself. In certain models, changing entanglement relationships mathematically changes the structure of space. That does not mean human thoughts create galaxies or that observation magically builds the universe around us. Those claims go far beyond the evidence. Instead, the research hints at something subtler, more scientifically grounded. The universe may be more relational than classical physics once assumed. Rather than reality being built from isolated objects existing independently in fixed space, space itself may arise from networks of quantum relationships and information. If true, this would represent one of the biggest shifts in scientific understanding since Einstein replaced Newton's fixed universe with space-time relativity. But physicists are still investigating these ideas carefully. The U-holographic principle is powerful because of its mathematics, not because it confirms mystical conclusions. It offers a promising path toward understanding quantum gravity, black holes, and the deep structure of reality. And even if future discoveries modify or replace it, the questions it raised have already changed physics forever. What if space is not the stage on which reality happens? What if space itself is part of the story physicists are still learning to read? After a century of quantum mechanics, one fact has become impossible to ignore. The universe is stranger than classical physics ever imagined. And yet, despite thousands of experiments and extraordinary technological success, physicists still disagree about what quantum mechanics is actually telling us about reality. That uncertainty is where many popular explanations drift into exaggeration. Some claim quantum physics proves consciousness creates the universe. Others argue that reality is entirely mental, that all U separation is an illusion, or that human observation magically determines existence itself. But the actual science is both more careful and more interesting than those claims suggest. Quantum mechanics unquestionably shows that microscopic systems behave differently from ordinary objects in daily life. At small scales, particles are described by wave functions, mathematical structures that encode probabilities for different possible outcomes. Before measurement quantum systems can exist in U, combinations of possible states known as superpositions. When a measurement occurs, only one outcome is observed. Exactly what this means is still debated. Some interpretations argue the wave function represents real physical possibilities. Others treat it as a mathematical tool describing information or probabilities. The many worlds interpretation proposes that all outcomes occur in branching histories. Relational quantum mechanics emphasizes interactions between systems rather than absolute standalone properties. But none of these interpretations have conclusively won. Importantly, quantum mechanics does not require conscious human observers to function. In physics, a measurement does not necessarily mean a person looking at something. It usually means any interaction that transfers information from one system to another. A photon striking a detector counts as a measurement. An atom interacting with its environment can count as a measurement. Consciousness is not required for quantum equations to operate. This point is often misunderstood. The word observer in quantum physics sounds psychological, but in most interpretations, it simply refers to physical interaction. That distinction matters because it separates established science from speculative philosophy. Another common misunderstanding involves entanglement and the early universe. It is true that all matter in the observable cosmos emerged from the hot, dense conditions following the Big Bang. In that broad sense, everything shares a common cosmic origin, but that does not mean all particles remain strongly entangled today in any practically meaningful way. Quantum systems are fragile. Interactions with the surrounding environment rapidly destroy coherent quantum behavior through a process called decoherence. This is why quantum effects dominate atomic scales, while ordinary human experience still appears stable, classical, and localized. A baseball does not behave like an electron because it's you. Quantum coherence is lost almost instantly through countless environmental interactions. Decoherence helps explain why the world appears classical even though its underlying rules are quantum mechanical. And yet, despite these clarifications, the deeper mystery remains. Bell experiments demonstrated that reality cannot be fully described through classical, local hidden variables. Quantum mechanics continues to predict experimental results with astonishing precision. The holographic principle and U-related ideas suggest spacetime itself may emerge from deeper formational structures. Taken together, these discoveries point toward a universe fundamentally different from the mechanical picture imagined in earlier centuries. Classical physics treated reality like a giant machine built from separate parts moving through fixed space and time. Quantum physics paints a subtler picture. At microscopic scales, reality appears woven from probabilities, relationships, and quantum states that do not. You fit neatly into ordinary intuition. Objects are not always independent in the classical sense. Space and time may not be fundamental. Information may play a deeper role than previously imagined. But science has not yet reached a final answer about what all of this ultimately means. And that is important. Modern physics is incredibly powerful because it distinguishes between experimentally verified results, theoretical models, and philosophical interpretation. The experiments are real. The mathematics is real. The technological achievements built on quantum theory are real. Your smartphone, computer chips, MRI scanners, lasers, atomic clocks, and GPS systems all depend on quantum mechanics functioning exactly as physics predicts. What remains uncertain is the deeper interpretation of the theory itself. That uncertainty is not evidence that anything goes. It does not justify replacing science with mysticism or speculation presented as fact. Instead, it reflects something profoundly human about scientific discovery. We have learned enough to know that reality is stranger than we expected, but not enough to fully explain why. And perhaps that is the most remarkable part of all. The greatest experiments in modern physics did not simply reveal new particles or equations. They revealed the limits of human intuition itself. The universe is not obligated to match the mental pictures evolution built for survival on a small planet. It only has to behave the way nature behaves. And so far, quantum mechanics remains the most accurate description humanity has ever found. Mysterious, incomplete, experimentally unstoppable, and still unfolding at the frontier of knowledge.